All right, guys, welcome to Discrete Math. Hope you're doing well. All right, so this unit is going to be unit 2.3. So this is about Hamilton paths and circuits. So let's review real briefly. Okay. So last time we talked about Euler paths in circuits. So Euler is where it's a path that uses every edge. So remember, every edge is every line. Okay, of the graph exactly once and once only. It starts and stops at different locations, and you have exactly two odd degrees. An Euler circuit is similar. You go over every edge one time and one time only. You start and stop at the exact same vertex for Euler circuit, and there's many solutions for this. Okay, but as a result of that, and the key on that is if all of the vertices have an even degree, then you know for a fact it's going to be an Euler circuit. All right, so that gets us into today's. Today's is talking about Hamilton. So Hamilton is similar, except it's a little bit different. So for that, Hamilton circuit's path, it's used, the book has this, it says that you examine fire hydrants on corners of streets. It's not really used a lot. It is true. The first person who actually did that was, oh my gosh, I just forgot. Ben Franklin, yes. He started fire hydrants in Philadelphia, so he started the first fire department up there. So anyway, he had that in one of his books. It's also used in computers, and that's what we're talking about because it's a computer science class. And it's also ranking for football players. Okay, I wouldn't use it really for that, but these are applications of where they're used. All right, so now we get to the next part. Is Hamilton came up with this, and his full name is Sir William Rowan Hamilton. Okay, he created what's called the Icosian game, and it's really about optimal route. And he had this, and it was a game, sort of like Nintendo or Wii or something like that today. But he started with this, and it was a board game, and there were pegs, and you use pieces of string. And it was how many, or what's your route to go so you can hit every single city. That's what these pegs were cities, okay? 20 major cities in Europe at the time, and that's what was in the Icosian game. It was actually pretty expensive. It is the equivalent of like paying about $10,000 for a game today, okay, which is way too expensive. All right, so now here's a blow up of it, if you want to pause it and draw it. But this is a Hamilton circuit, okay? So what you have to do is I can start anywhere, okay? So I'm going to say, well, I'm going to start here. So I'm going to say I'm going to start here. And a Hamilton circuit means that I start and stop at the exact same location, okay? So what I'm going to do is I'm going to go through every vertex, okay? Before we had to go through every edge, okay, every line. I'm not doing it this time, okay? I'm only going through the vertices, okay, just the vertices. So for instance, I can go, so I got that one, go, 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 go. Go, 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 go. Let's see here. Whoop, oh, I messed up, so let me try it again. I know I can do this. So let's see here, I'm gonna go, 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 go. I'm going to go up here, through here. Let me try again. Sometimes it's a little tricky. Well, can't believe I'm messing up. So let's see here. Aha! So I found it. I mean, it takes a little bit of time. It's not that big a deal. All you have to do is just erase and start over and try something different. Okay, so anyway, I went up through this, okay, I eventually looped around and I ended up stopping. Well, I wrote start again. I ended up stopping exactly where I started, okay, and that's really a Hamiltonian circuit. All right, so what about this? Well, this actually is really used a lot in computer science. So you have two things. You have two things that are really a big deal. Okay, so you have a Hamiltonian path, and that's one of those things where you start and stop at different vertices. Okay, but no matter what, it has to be different vertices. Okay, a Hamiltonian circuit is where it starts and stops at the exact same one. Now the key on this is that you have to look for Hamiltonian circuits first, okay? A path is usually pretty common, so you gotta look really, really hard and see, okay, is there really a circuit somewhere in that? If there's a circuit, then you just gotta find it, okay? And just slowly take your time, just be very methodical in finding it. If it's a path, well, that means there's no circuit, okay? And the hard thing about this is there's no trick. Like in Euler, you know, we looked at degrees. Now there's honestly no trick in this one. So you've got to go slow. There's no known algorithm. So a lot of computer scientists, it has to actually have a Hamiltonian circuit. And the reason for that is, like when you're on a laptop, whenever I press a button, okay, or a key, it shows up in a different spot. Okay, so that's a Hamiltonian path. And that's it's a little bit easier to have a laptop than it is to have a cell phone. On a cell phone, your touch screen is exactly where you put your finger. So that is a Hamiltonian circuit because it wants to start and stop at the exact same point. That's why it took a lot longer to develop a smartphone, because you press it and it shows up exactly where that spot is. Okay. So anyway, that's it's an example of a Hamiltonian circuit. But anyway, it's really hard, and you got to think through exactly where those are. All right. So let's talk about this real quick. So let me give a couple of examples. So for example, if I have A, B, C, D, and E, and I'd suggest writing these down. Okay. So let's say that I've got something that goes like this. Okay. So if you look and say, okay, where can I start? Well, I'm going to start at B, and you just got to play around with it. Okay. If I start at B, then can I go around? Well, no matter what I do, if I go this way, I can't get back to B, okay, because I cannot go through D again. So I could go there and end up at C. I could go this way, and actually I can't go that way because I've got to go back to A somehow. So it looks like this example right here is going to be a Hamiltonian path, because if I start at a spot, well, let me just change spots. What if I start at D? Start at D. Well, if I do that, then I can't go to C and then back. Okay, I can't go this way because I can't get to B. Because remember, on a Hamiltonian circuit, you have to go to every vertex one and one time only. So there are a couple different ways that you could do it. I could have a Hamiltonian path. And there's quite a few paths that I could have. I could go A to B to D to C to E. Okay, so I could go this way, C, E. Okay, so I could go that way. I could go B to A to D to C to E. Okay, and yeah. There's about 3 or 4 more. Okay, that you could do. So let's say, well, what if I have something that's slightly different? Okay, and you want to see if it's Hamiltonian path or a Hamiltonian circuit. So if I have like A, B, C, D, and E. Okay, and let's say I've got something like this. All right. So what can you do? Honestly, the best way is this is going to end up being a Hamiltonian or a Hamilton circuit. And the easiest way I can say to do it is if you can literally go on the outside edge. If you can go on the outside edge and loop it around, then you really can do it. Okay. The other one I've seen that's pretty tricky. I just want to make sure that this is on there. Is, and remember, you don't have to have all the edges. Okay, so if I had A, B, C, and D, E, and let's say I've got something like this. So how can I go? Oh, and like something like that. Okay. So how can I go? Okay. So I'm looking at it and I can't go all the way around. Okay. So what I would do is I would say, okay, let me start at D. Okay. If I start at D, I can actually go. I can go up and around, okay? So it's like I'm going on the outside loop, okay? So I could go from D to E to A to C. Now the key here is I can't go C to D, but I do need to go to B. So I actually can go this way to B to D. So notice that I started and stopped at the outside, okay, are the exact same. So start and stop are the exact same. So this is a Hamilton circuit, okay, which is a good thing. That's exactly what you want. It really is a good thing. All right, so anyway, those are some examples. All right, so now, what else is going on with this? You can use this as a tournament, okay? Directed arrows show winners and losers. Every tournament contains at least one Hamiltonian path. So in every tournament, someone's got to win. Okay, someone's got to win. Use the Hamiltonian path to rank the teams in order from winner to loser. You draw a diagram to represent the tournament, find a Hamiltonian path, and then you rank the participants. Okay. All right. So what is a sample tournament? So let me draw this. So if I have A, B, C, and D, we'll just do something real quick. So if I've got, like, let's say that A beats everybody. Okay, I've got that B beats D, B beats C. Okay, so remember that this is A, and if it's going like this, the way to think of it is that A beat B. All right, so that's the way you want to think about exactly what's going on here. All right, so what am I missing out on? Oh, C. Let's say that C beats, actually D beats C. Okay, D beats C. All right, so what's happening here? So I've got A beats everybody. So I'm going to say A is greater than B. Okay, B beat both of these. Okay, well, actually, who lost? Who lost all of them? C lost. C is way over here. It's the ultimate loser. Okay, A is the winner. Okay, and C, who's the only person that beat C? Well, D beat C. So this is actually your pathway, okay, for this tournament. So if we look at it, let me highlight in green. So I'm saying that A goes to B, it goes to D, okay, and D beat C. So what's in green is the Hamiltonian path, and this would be the path for this scenario. Okay. All right. So the other thing that we need to know is Let me erase this so you can see it real good. All right, so a transmitter is a vertex with a positive out degree and 0 in degree. A receiver is a vertex with a positive in degree and a 0 out degree. So let me draw one of these. So if I've got an A, B, C, okay, let's say A beats both of them and C beats B, okay. So remember that if I'm drawing this, so I've got A, I've got in degree and out degree, okay. So remember this is going out or away, so A has 2 out degrees, okay, and 0 in degrees. B has 2 in degrees, 0 out degrees, and C has 1 in 1, okay. So which one of these would be considered a transmitter, a vertex with a positive out degree and a 0 in degree? So A is going to be the transmitter. Okay, so it's a transmitter. I'm hoping that you can see that. Let me just put a little bit more so you can see it. Okay, so A is going to be the transmitter. A receiver is going to be B. Okay, so it's going to be the receiver on that. And I think that's pretty much it. I would just look through the videos. Hopefully that helps. Anyway, that's it for the day. So let me give you the quote of the day. So this is by Sir Ian Hamilton, okay, who we just talked about. Propaganda as an inverted patriotism draws nourishment from the sins of the enemy. If there are no sins, invent them. And that's it's a way to look at things. All right. So anyway, you have a great day, and I hope this makes sense. Maybe not the quote of the day, but I hope the rest of the lesson does. If not, be sure to write down your notes and go back and look through, and then try the practice. All right. Thank you very much. Bye.